Carbonyl compounds undergo nucleophilic addition. In this video, we will begin by looking at the reactivities of the carbonyl functional group in relation to the mechanisms of nucleophilic addition. The chemical properties of the carbonyl compounds is closely associated to its functional group. The C double bond O is saturated, comprising of a sigma and a pi bond. The pi bond can be easily broken to allow addition reactions to take place. In addition, the oxygen atom is more electronegative than the carbon atom. Due to oxygen atom drawing the electron clouds away from the less electronegative carbon atom, the carbonyl carbon becomes electron deficient. Therefore, it is susceptible to attack by nucleophilic reagents such as the nitrile anion and lithium aluminum hydride. Nucleophiles such as nitrile anion are chemical species that are attracted to the electron deficient centers. During a nucleophilic attack, the nitrile anion donates its lone pair of electrons on carbon to the electron deficient carbonyl carbon atom. Although there is another lone pair of electrons on the nitrile anion, it is more difficult for the nitrogen atom to donate its lone pair due to its higher electronegativity. In the last video, we have seen the nucleophilic addition reaction. In this reaction, the HCN molecule is added across the double bond of the carbonyl compound to form cyanohydrine. Cyanohydrine is also known as hydroxynitrile. For nucleophilic addition to occur, the initial generation of Cn- is required. To provide sufficient nucleophiles for the reaction, a small amount of alkali, NaOH or KOH, or a small amount of cyanide salt, NaCN or KCN, is added. By adding a small amount of alkali, some HCN will be neutralized to give Cn-. Note that adding too much alkali could react away all the HCN required for the reaction. If KCN or NaCN is added, they will dissociate completely in water to give Cn-. Following the generation of nucleophiles is a two-step mechanism involving the carbonyl compound. The first step shows that Cn- is acting as a nucleophile. The second step shows the regeneration of Cn-. This explains why only a small amount of Cn- is required for the reaction. For presenting the mechanisms of nucleophilic addition, note that you must present the relevant method used to generate the nucleophile on top of this two-step mechanism. Let us examine the details in the two-step mechanism more closely. Due to the higher electronegativity of oxygen, the carbonyl carbon is electron deficient. This is shown by the partial charges. Being a nucleophile, Cn- donates its lone pair of electrons on its carbon atom to the electron deficient carbonyl carbon. For the carbonyl carbon to retain its octet structure, the pi bond is broken, with its pi electron given to the oxygen atom. After this slow step, the oxygen atom now bears the negative charge. The intermediate from step 1 has a lone pair of electrons on its negatively charged oxygen atom. In step 2, this lone pair of electrons on the intermediate is used to grab a proton from HCN. This fast step produces the cyanohydrin, and Cn- is regenerated. The reaction is extremely slow if only HCN is used. This is because, other than the carbonyl compound, the rate-determining step involves the nucleophiles. Rate study of this reaction confirms that the rate is directly proportional to the concentration of Cn- as shown by the rate equation. But HCN is a very weak acid which remains largely undissociated. With the position of equilibrium for the acid dissociation lying largely to the left, the concentration of Cn- from HCN is very low. The addition of a small amount of base such as NaOH or KOH helps to increase the rate of reaction. By neutralizing some acid, the position of equilibrium is shifted to the right to produce a higher concentration of Cn-. The addition of NaCN or KCN also helps to increase the rate of reaction. NaCN dissociates completely in aqueous solution, resulting in a higher concentration of Cn-. As HCN is highly toxic and boils at 26 degrees Celsius, it is safer to generate HCN in situ. This is done by reacting a small amount of dilute sulfuric acid with NaCN or KCN. Next, we will look at how the reactivity of carbonyl functional group is affected by remaining structure of the molecules. Differences in structure can give rise to varying rate of reaction under the same reaction condition. Generally, the aldehydes are more reactive than the ketones towards nucleophilic addition. We can explain the difference in reactivities using the inductive effect by alkyl groups as well as the steric effects. Methanol is the smallest aliphatic carbonyl compound. It has no alkyl group bonded to its carbonyl carbon. Other aliphatic aldehydes have one alkyl groups, whereas aliphatic ketones have two. With more electron-donating alkyl groups, the carbonyl carbon will be less electron deficient. Due to this increasing inductive effect, the carbonyl carbon becomes less attractive to the nucleophiles. Since the carbonyl carbon of ketone is the least electron deficient, it is the least reactive towards nucleophilic addition. The alkyl groups are significantly larger than the hydrogen atom. Such bulky group blocks or hinder the nucleophiles from approaching the electron-deficient carbonyl carbon. Increasing steric effects decreases the frequency of effective collision between the carbonyl and the nucleophiles, thus resulting in lower rate of reaction. The larger the number and size of alkyl group, the more significant is this steric effect. Therefore, carbonyl compounds with the largest alkyl group in numbers and size will therefore be the least reactive. Aromatic carbonyl compounds are generally less reactive than aliphatic carbonyls towards nucleophilic addition. The reactivity is affected by the number of phenyl rings attached to the carbonyl carbon. The aromatic compounds react at a slower rate compared to the aliphatics. Compounds with more aromatic phenyl rings also react more slowly. How does the phenyl ring affect the reactivity of carbonyls? For phenyl rings that are directly bonded to the carbonyl carbon, the delocalization of pi electron systems of the benzene ring will be extended over to the C double bond O group. Due to this resonant effect, the carbonyl carbon is now less electron deficient and therefore less attractive to the nucleophiles. This explanation, based on the delocalization of pi electron, is commonly used in the syllabus to explain the properties of aromatic compounds. For example, the reactivity of phenol and the stability of benzoate anion. Last but not least, we will look at the stereochemistry involved in nucleophilic addition. Any carbonyl compounds with two different groups attached to the carbonyl carbon will give a chiral cyanohydrine after nucleophilic addition. Would you expect the products to be a pure enantiomeric form or a mixture? To understand the stereochemistry of products, we need to visualize the reaction mechanism in 3D. Let's begin with the carbonyl carbon, which is sp2 hybridized. Note that the arrangement around this carbon is trigonal planar. Due to this flat planar arrangement, the nucleophile can attack this carbon center from either the top or the bottom of the plane with equal probability. Let's look at an example. When the nucleophile attacks the carbonyl center of butanone from the top of the plane, all three groups on the plane will be pushed downward due to electronic repulsions with the new bond pair. This gives rise to one enantiomeric form as the product. When the nucleophile attacks from the bottom, all three groups on the plane will be pushed upward. Again, this is due to the electronic repulsion with the new bond pair form. This gives rise to another enantiomeric form. Note that these two products are non-superimposable mirror images of each other, and together they form a racemic mixture. A resultant mixture containing equal amount of each enantiomers is known as a racemic mixture. We can confirm the formation of racemic mixture since the mixture of chiral cyanohydrine is optically inactive. Each enantiomeric form of cyanohydrine rotates plane polarized light in an equal but opposite direction. The optical activity of one enantiomer cancels out the optical activities of the other.